In this lesson, I'm going to be talking about compliance and resistance. This is a big one for both A&P and mechanical ventilation, so let's dig in. We'll start with resistance. You really need to think about resistance as airflow through the airways. When I have an intubated patient, that's going to include the circuit, your ET tube, all the way through your airways, your conducting airways, down to the respiratory zone. Once you get to the respiratory zone, that is going to be more compliance. So when you're thinking about what causes an increase in airway resistance, we're kind of going back to Purcell's law, where radius is going to matter significantly. So, what would decrease the radius of my airway or obstruct flow? Mucus and secretions in the conducting airways, your HME or in your circuit, bronchospasm or inflammation, a kink in the ET tubing, biting the ET tube, a clogged HME, which should be right about here, and of course, water in the circuit. We're talking about normal airway resistance. We're looking for it to be about 0.8 to 2.4 centimeters of water per liter per second, but that is if you have a non-intubated patient. What we're more concerned about in mechanical ventilation is an intubated patient with an artificial airway. That artificial airway is going to reduce the radius of the airway, and so resistance is going to increase to closer to at least 5 to 6 centimeters of water per liter per second. But we're going to consider anything greater than 10 to be high. We're not really concerned about low resistance in this patient. We're concerned about high resistance. So if I have that, what should I do? The first thing you're going to do is look at the circuit. Is there water or secretions somewhere in the circuit or the HME? You're also going to listen to breath sounds. If they have rhonchi, that would suggest that there is mucus present and you need to suction. If they have wheezing, then it's because of bronchospasm and you need to give a bronchodilator. It's also important to understand how raw is going to affect values in pressure control or volume control. If I am in volume control, volume is set, but pressure is variable. That means that if the patient has an increase in raw, it's going to be harder to get that volume into the patient's lungs. And so peak pressure is going to go up. So you're going to have an increase in peak pressure in volume control mode. If I'm in pressure control mode, then I am controlling pressure and my volume will be variable. The patient will potentially get less volume for that same amount of pressure. So I'm looking for a potential of a decreased tidal volume if there's increased raw in pressure control. The other thing that you're going to need to note is that there is an increase in trans-airway pressure. This is going to be PIP minus PLAG, and that's going to be part of our equation. Now let's switch to compliance for a moment. Compliance is the ease of inflation of the alveoli. We're really looking for changes in either alveolar or chest wall compliance. So you need to ask yourself, what would prevent inflation of the alveoli? Really tie alveoli and chest wall compliance into your mind when you're thinking about compliance. And when I say compliance, at this point, I'm really talking about static compliance. So anything that's in the alveoli, fluid or secretions, which can be caused by pneumonia, pulmonary edema, consolidation, which is also with pneumonia, as well as atelectasis. ARDS is a big one. In fact, it's actually called stiff lung disease because it has such a decrease in compliance. But it can also be something that is pushing against the alveoli. So it's going to be an issue inside the alveoli themselves, like here, or it's going to be pushing against the alveoli. So something like a pneumothorax or hemothorax, a pleural effusion, abdominal distension, obesity, certain chest wall deformities like kyphoscoliosis, where they're kind of hunched down. All of those things are going to affect the ability of the alveoli to inflate only because it is pushing against the lungs. Normal compliance is about 100 mLs per centimeter of water when we're not on mechanical ventilation. But when we add positive pressure, we are going to see a reduction in compliance to about 35 to 50 mLs per centimeter of water. Again, I'm less concerned with increased compliance than I am with decreased compliance. but sometimes there are test questions about what causes an increase in compliance. And there are two things that you need to be aware of. The first is flail chest, and that is because we have less chest wall stability when we have a set of fractured ribs. The second one is emphysema. This is because of a loss of elastance. Elastance is the force that works against compliance. It's the part of the lungs that helps bring it back into a resting state. You can kind of think about that as a rubber band. We stretch it out, and if we stretch it out too much and we keep stretching it out over time, that rubber band loses its elastance or ability to come back. So without that elastance, we can see an increase in compliance. Sometimes this is a test question about what causes an increase in compliance. Other times emphysema is given as an answer. Make sure that you don't choose it for decreased compliance. So if I have a decreased compliance, what should you do? The first thing that you may look for is to get a chest x-ray. This is really to evaluate the disease process that could be occurring, since our compliance issues are mainly happening as an alveolar disease or something pushing against the alveoli like a pneumo or a pleural effusion. So we may get a chest x-ray to evaluate what's going on. There may be more assessment in a question that tells us what to do, or the last thing is to increase PEEP. We're going to increase PEEP to recruit alveoli since that is a common cause of decreased compliance. So it may be to increase PEEP or to do a recruitment maneuver. When it comes to understanding what is happening in modes, we need to really watch plateau pressure in volume control mode. Plateau pressure is going to be my pressure for compliance, and that's the one that I'm going to look at first. We're going to talk about that in a minute. So when we're in volume control, we're going to have an increase in both PIP and plat. And when I'm in pressure control, the same thing is going to happen as if I had an increase in resistance. It's going to be harder to get that volume into the lungs, and I'm keeping pressure the same. And so tidal volume is going to decrease in pressure control mode. Now we're going to jump back into airway resistance, particularly the calculation of it. And remember that we're going to use transairway pressure, or PIP minus plat. And remember that airway resistance is resistance of airflow through the airways. And so that should help you remember that we're going to use flow rate in the equation as well. So PIP minus plateau divided by the flow rate will give us our answer in centimeters of water per liter per minute. Then we're going to multiply by 60 to get liters per second. You can convert your flow rate ahead of time, but I do find it's easier for students to plug their numbers in and then multiply by 60 at the end, because there are multiple calculations in mechanical ventilation where we're going to do this. So remember that if you see increased trans-airway pressure, it is an increase in airway resistance. There will be no change in plateau pressure. So let's do a calculation here with 45 liters per minute. I'm going to go ahead and start my baseline pressure at 5, since that's often a normal baseline pressure. My peak pressure is going to go up to 20 centimeters of water. I'm going to do an inspiratory hold. That is what is going to give me plateau pressure. And I'm going to drop down to 15, and then I'll return back to my baseline pressure when I let the breath go. So when I'm doing my calculation, I'm going to be doing that peak inspiratory pressure minus my plateau pressure. So really notice that what I'm looking at is going to be the difference between peak and plat. I'm going to divide by my flow rate of 45 liters per minute and then multiply by 60. Make sure that you do 20 minus 15 first, then divide by 45, then times 60. That will give you an answer of 6.7 centimeters of water per liter per second. So let's calculate it when we have an increase in trans-airway pressure or an increase in raw. So this time my peak pressure is going to go up to 30 centimeters of water, but when I do my inspiratory hold, I'm still going to fall back to 15 because it will not change when it's airway resistance. And then I'll drop back down to 5. When I do my calculation, we'll do 30 minus 15. That is the difference between here and here. And then divide by 45. then multiply by 60. That will give me 20 centimeters of water per liter per second. So this is a very increased raw. If I'm looking at it graphic wise, I can tell that it's an increase in raw even without doing my calculation, because I see that I have a very small difference here and it has increased here. So remember that the difference between here and here, is trans airway. Now let's do static compliance. Remember, static compliance is going to be the true compliance of the lungs when I'm talking about alveolar compliance. So that is why I need plateau pressure, because I'm looking for pressure with no flow that's going to give me intrapulmonary or alveolar pressure. And so my equation is going to be tidal volume divided by plateau pressure minus PEEP. It's always going to be volume over change in pressure. You may be asked to use corrected tidal volume. I'm going to do a slide on that at the very end, just in case you are being asked to do that. Not every program does. It's important to note that with compliance, both our PIP and our PLAT is going to change. So let's take a look at it on our pressure graph. And we're going to say that our tidal volume is 500. We would need a volume graph in order to actually see that, or we have to know what we have set. So for this first patient, we're going to start again with our baseline of 5. And we're going to potentially still have that situation kind of in the beginning. I think we went up to 20, and then we had a plateau pressure of 15, and then down. It's important to really be able to recognize peak pressure versus plateau pressure. Make sure that you are using plateau pressure here. So I'm using this value. So when I do this, I'm going to be doing 500 divided by 15 minus my baseline pressure of 5. So 500 divided by 10 is going to be 50 mLs per centimeter of water. Now let's look at what happens when we have decreased compliance. So this time, what would potentially happen is that my peak pressure is going to go up, but it's not part of my equation. I'm really looking at just where is my plateau pressure. It's going to hit 20, and then it's going to go down. So what you're going to notice is that both peak pressure and plateau pressure have gone up, but what hasn't changed is the difference between PIP and PLAT. That would be airway resistance. I know that compliance has changed because my plateau pressures have increased. But if you want to go ahead and calculate this one out just to see how much it has decreased by, we're going to take that same tidal volume of 500, but this time divide by 20 minus 5. That's going to give me 33 mLs per centimeter of water, and I can tell that that is decreased compliance. And finally, we're going to talk about dynamic compliance. Dynamic compliance is going to be affected by both static compliance and airway resistance. And so you really can't necessarily tell what you are dealing with until you look at both of those values together. Dynamic compliance is the pressure that is needed to obtain the volume during inspiration with flow. And so our compliance calculation is still going to be volume over pressure, but this time we're going to use peak inspiratory pressure instead of plateau. It's important to remember that my dynamic compliance is always less than static compliance. So if you see something that puts dynamic compliance higher, then you've either done your calculation wrong or somebody's recorded the results or the calculations wrong. So let's do that calculation. I'm going to start with a situation similar to where we had that increased airway resistance. So we'll have our baseline of 5, and we went up to 30, and then we had a plateau pressure of 15, and we went to 0. It's very important that when you're calculating dynamic compliance that you leave plateau pressure out of it. It may give you a graphic that has plateau pressure, or it may give you a question that has plateau pressure in it, but we're not going to use plateau pressure here. We're going to use peak inspiratory pressure. So tidal volume is still 500. We're going to take 500 divided by 30 minus 5. That will give us 20 mLs per centimeter of water. Let's do the same here, but this time we'll make it more of a compliance. We'll do up to 25. And then we're going to come down. Let's just come down to 20. Doesn't actually matter what our plateau pressure is, but I want to give you a sense of what happens when our compliance has increased, but we don't have an increase in airway resistance. But I'm still really focusing just on that peak inspiratory pressure. And so here I'm going to do 500 divided by 25 minus 5, and that will give me 25 mLs per centimeter of water. So again, whenever you're using dynamic compliance, just keep in mind that this does not tell you whether it's an increase in airway resistance or a decrease in static compliance. We need to actually look at static compliance with dynamic. And so we often look at trending. So this is our first example of trending. When we say trending, we are looking at values over time and seeing how they change and what could that possibly mean. It may give you pressures or it may give you the compliance numbers. We're going to start by looking at pressures. And so you can see that I have time and I have PIP and I have plat. We're always going to look at plateau pressure first. If plateau is changing, that means that compliance is changing. My next step is to determine whether it's a good or a bad thing. And so here you need to remember that increasing pressure is bad, decreasing pressure is good. If it takes more pressure to get volume in, that means that my lungs are stiffer. If I have decreasing pressure, it means it's easier to fill the lung. So then I'm going to attach good or bad to the compliance. Bad compliance, decreasing compliance. Good compliance, increasing compliance. So that's kind of the steps that you want to go through initially. Once you practice these a while, you'll be able to do it more easily. But this is usually how I find that people learn it best, by determining what is happening, remembering what's good and bad, attaching that good or bad, and then making your decision. So here we say that increasing plateau pressure means that we have a compliance change. It is going up. An increased plateau pressure is a bad thing. It's taking more pressure. My bad compliance thing is a decreased compliance. And so that is going to be my answer. And I could be potentially looking for decreased compliance as the answer, or I might be looking for an example or a disease state that is causing decreased compliance. One important thing to note is that trans-airway pressure is stable, meaning the difference between those two values is remaining the same. You'll note that peak inspiratory pressure is also increasing, but it's increasing by the same amount. Okay, we're going to do this again. Once again, we're going to look at plateau pressure first. But my plateau pressure isn't changing. And if these values change by 1 or 2, that usually still doesn't count as changing. So right now, my plateau pressure is staying the same. If plateau pressure isn't changing, then it has to be airway resistance. So we're still going to determine, remember, what's good, what's bad. Increasing pressure is bad. Decreasing pressure is good. So we're going to attach that good or bad to raw. Bad raw is increased raw. Good raw is decreased raw. Here, plateau pressure is not changing, so we know that the problem is airway resistance. We also know that we have an increased trans-airway pressure. That also means a bad airway resistance. Bad airway resistance is when it's increased. We have an increase in airway resistance. That is not a good thing, and so that is my answer. Again, I could be looking for that just straight as the answer, or I could be looking at it as which of the following is a cause of increased airway resistance, or I could be looking at which of the following would you do, and you're going to want to look for an answer that would potentially decrease airway resistance. So again, note that this is staying the same, but this number is increasing. And so the difference between these two values is increasing. Let's trend again, but this time with dynamic compliance and static compliance. And so my static compliance, remember, that is going to be essentially using my plateau pressure. This is going to be peak inspiratory pressure. So if it helps to write that beside there, you can. Just like before where I use plateau pressure first, I'm going to look at static compliance first. If static compliance isn't changing, then it isn't a compliance issue. It has to be airway resistance if my dynamic is changing, and it is in this case. So we still have to kind of determine the good or bad parts of this. Remember that an increasing compliance is a good thing, a decreasing compliance is a bad thing. And then we're going to attach that good or bad to airway resistance in this case because we know compliance is not the issue. So a bad airway resistance is increased, a good resistance is decreased. So let's take this step by step. We're looking at static compliance first. Static compliance is remaining at 40. I come and I look at dynamic compliance. Dynamic compliance is actually increasing. An increased compliance is a good thing. When I attach that to airway resistance, a good airway resistance is a decreased airway resistance. And so decreased draw is my answer. I'm looking for a potential improvement in this patient. You'll also notice that the dynamic compliance and the static compliance have a decreased difference between them. The lower that difference goes, the better my resistance is. One more time, we're going to look at static compliance and dynamic compliance. We're again going to look at static compliance first. We're going to see that our static compliance is changing, and so we know that this is a compliance issue. Dynamic compliance is going to change also, but it doesn't matter. The main thing that I'm concerned with is the fact that my compliance is changing. We're still going to attach good or bad. We're going to attach good or bad to compliance. So I'm going to walk you through this step here. So I have static compliance. Static compliance is decreasing. A decreased compliance is a bad compliance. It means that my lungs are stiffer. A bad compliance is a decreased compliance. You'll note that if you do want to look at the difference between those two, they are changing by about the same amount. The very last thing that I'm going to talk about is tubing compliance, or finding corrected tidal volume. This is not something that every program does, but if yours is one that has you do this, this is how you do it. So we're taking tubing compliance and finding the amount of volume lost within the circuit. Because the circuit has a certain amount of distendability, whenever we provide positive pressure to it, it's going to expand and we're going to lose a little bit of that volume. Now the ventilator really does this calculation and automatically compensates for it, but traditionally we would, or old school wise, we would have to actually calculate it out. So the calculation for tubing compliance is still a compliance calculation where we're taking volume and dividing it by pressure. This is normally found during a pre-ventilator check where you're going through and making sure that the ventilator is working correctly. So when we cap it off, we are looking at how much volume we can get for a particular pressure. So for example, if we had 100 mLs and a pressure of 50, we would take that 100 and divide by 50 to get a tubing compliance of 2 mLs per centimeter of water. Once you have that tubing compliance and once on the patient, you're going to use the peak inspiratory pressure that is measured to find the amount of volume loss. The equation for volume loss is going to be tubing compliance times peak inspiratory pressure. So if we have a tidal volume of 500 mLs, a PIP of 20, and a tubing compliance of 2, we're going to take that tubing compliance of 2 and multiply it by a PIP of 20 to get 40 mLs of volume loss. That means that 40 mLs are essentially like lost in the circuit or stuck in the circuit. And so our tidal volume is actually going to be decreased, and that's why it's called corrected tidal volume. So our corrected tidal volume is taking the volume that we have and subtracting out how much loss there was. So if we have a tidal volume of 500 mLs and we subtract 40, we will get a corrected tidal volume of 460 mLs. So if you want to do some more practice, head over to www.myBRESP.com. There I have a whole interactive ventilator study course on the website. In this introduction part 1, you can actually go in and find an introduction to compliance and resistance. This is unlocked and free as long as you create an account with an email. In here, I will introduce you to the calculations in for static compliance and resistance, but I do get into a deeper dive when we get to the measurement section, which is in intro part 2. If you have any questions, please find me on Facebook. You can go to the website. My email address is there. You can also look up RT Study Hall on Facebook.